Welcome to EE World. I'm Martin Rowe. Wi-Fi 6E adds 1200 megahertz of unlicensed spectrum to be available for Wi-Fi use. That spectrum, covering 5.925 gigahertz to 7.125 gigahertz, will add considerable capacity to the ever-growing needs for Wi-Fi. The so-called 6 gigahertz band is, however, not without incumbents, and those incumbents include public safety, wireless backhaul, TV broadcasting, and other uses. Therefore, we need some way to share that spectrum. Wi-Fi 6E has two power levels, a low power level, which is for the consumer items such as phones, routers, tablets, laptops, and so on. But there's also a standard power specification, which covers fixed uses such as stadiums, factories, arenas, and so on. To learn more about how that works, we spoke with Kurt Schaubach, CTO of Federated Wireless. Kurt will explain how the spectrum sharing works. Kurt, thank you for being with us today.
Of course, actually, Wi-Fi works in unlicensed bands, and it is a form of spectrum sharing where devices collaborate with each other and on a device-to-device basis through a contention-based protocol, listen before talk, actually share spectrum and coordinate. Wi-Fi has been tremendously successful because of the ease and simplicity of deployment, the low cost, the sort of use cases that it satisfies. It's hard to imagine a world that we live in today without Wi-Fi. But just as is true in mobile technologies, Wi-Fi and any unlicensed band technology in general faces challenges of where is the next opportunity for spectrum going to come from to expand services and capabilities. The roadmap for Wi-Fi technology calls for expanding channel bandwidths, improving, user throughputs. All of that requires more spectrum. And in order to do that, we need to get much smarter about how we approach bands that are already in use and find ways to take things like Wi-Fi or other unlicensed technologies and layer them in to those bands that might have, incumbent uses and be able to share spectrum, not only on a device-to-device basis, but between, say, different sort of categories of uses like Wi-Fi to incumbent uses. And we're going to see the first instantiation of that in the 6 gigahertz band. So a couple of years ago, the FCC created a 1200 megahertz of spectrum that is used by fixed microwave links and a variety of other incumbents. And they identified that this band was really an optimal band to be able to share that spectrum with new Wi-Fi uses and created the 6 gigahertz band for unlicensed use, and where Wi-Fi 6E technology is currently being deployed and will continue to be deployed. The Wi-Fi 6E band has both low power indoor and standard power AP devices. And our interest from a Federated Wireless perspective is in that second category of use, standard power devices, which standard power really connotes higher power operation in the band, outdoor operation, maybe some indoor operation like in large venues, factories, warehouses, where more power or higher performance out of an access point is beneficial. And in order for those devices, in order for those APs to operate, the requirement is that they connect to something that the FCC devised as part of the rulemaking process to coordinate and share spectrum, known as an automated frequency coordinator, or AFC. And Federated has really been leading the industry, pioneering the development of this automated frequency coordinator capability, working through the FCC and the standards bodies to get this developed and approved. So we're looking forward to basically taking the technology that we already developed for software-defined cloud-based spectrum sharing for the 3.5 gigahertz CBRS band, and applying a lot of that same know-how now for sharing spectrum in the 6 gigahertz band for new unlicensed uses, and hopefully finding ways to again expand that use of that cloud software platform and that technology domestically into new spectrum bands and internationally into the 6 gigahertz band as that gets adopted globally, and even other spectrum bands on sort of in the international theater.
Okay, for our audience who may not be familiar with how CBRS works. So CBRS, because it first of all, it's a licensed band as opposed, well, it's a licensed band in that carriers are going to use it. I believe there's also a certain unlicensed aspect to it. But regardless of whether it's licensed or unlicensed, you have incumbents. At least in the U.S., it's the U.S. Navy, and in areas near the coast where I live, that's an issue because the naval ships in the area might need to use that spectrum, and they get priority. And the way that works is there's essentially a database that gives the Navy priority over everybody else. There are actually three levels of priority, but the top priority is the U.S. Navy. And so if they need the spectrum, everybody else has to step aside, move to another channel, or just get off, whatever the case is. Now, in the case of Wi-Fi, that's a little different. So can you comment on that difference might work in terms of for Wi-Fi?
Happy to. So this, as you described, Martin, the CBRS band has multiple tiers of access. The incumbent tier, priority access tier, and general authorized access tier. Each tier has sort of different attributes associated with not only its prioritization and protection obligations, but the fact that, in particular, the incumbents in the CBRS band are dynamic. The primary incumbent, as you identified, is the U.S. Navy. They operate predominantly near the shoreline. They do have some inland locations. But what makes it unique is that their radars move around. Ships move around. The radars associated with them move around. They turn on and off. And the dynamism of that use needs to be accounted for or accommodated in the spectrum sharing platform. And that is necessitated use of both a sensing technology to detect when the Navy's operating, as well as some very sophisticated algorithms to assure protection and reassign users to other portions of the band as needed to assure, incumbent tier protection. Now, what's unique about the 6 gigahertz band, or different, if you will, about the 6 gigahertz band, is that first off, the incumbents are fixed in their location predominantly. There are some mobile uses, but for the most part, the vast majority of incumbents in the 6 gigahertz band are fixed point-to-point links. So their uses are, more static in nature, long term. They don't move around. There's not as dynamic a sharing environment in terms of how to protect incumbents. And also their locations are known through a database, accessible through the FCC, the Universal Licensing System. So the structure or composition of the sharing platform that we have for the 6 gigahertz band is greatly simplified compared to what's required for CBRS. Another key difference is that in the 6 gigahertz band, the protection criteria is based on what we would call single entry analysis, so that we don't need to aggregate the combined effects of, say, multiple Wi-Fi APs on a single incumbent in terms of determining protection. Where in CBRS, we have to do this aggregation of interference potential as we explore incumbent protection or examine incumbent protection, and that requires more compute resources and more sophisticated algorithms. So think of what we're doing with the AFC and 6 gigahertz is very similar in terms of it's cloud-based, it's software defined, it provides more determinism of access, it shares spectrum with incumbent users, but it's greatly simplified in terms of it doesn't have as sophisticated or difficult protection criteria. The users don't move around. All of these things make the platform itself much simpler, to develop, deploy, much easier from the quite frankly from the perspective of providing incumbent protection.
These microwave links, are they operating all the time, 24 hours a day?
Yep. Many of those links are used by the mobile network operators, by public safety systems, enterprises for communications backhaul. So a very prevalent use is providing backhaul to cell sites for mobile network operators over the 6 gigahertz band using microwave capabilities. So yes, those are operated long term. They're fixed services. They're known through a database, so we know how to protect them. Their characteristics that they operate at are well known, in terms of how they get licensed, that orientation of the dishes, the transmit powers, things like that. The key thing is, as you think about this highly focused beam of energy that, is transmitted between two dishes, and oftentimes above the clutter line, that leaves lots of spectrum available, sort of down in the clutter, below the clutter, for all sorts of uses that we know Wi-Fi takes advantage of today. So there's really an ideal scenario of these two different uses and network topologies, if you will, that make for Wi-Fi to be a great addition to this band, and a really novel way to increase the efficiency of spectrum use by effectuating the sharing.
Now, while we have focused beams between one tower and the next, or one tower and the network, they're not so focused that there couldn't be, or maybe it's the case of in the other way where the clutter is doing the interfering, which is certainly not focused beams. So there, even though you have this focused beam, you can still have some interference. So but where this focused beam is on 24 hours a day, it's not like in CBRS where the Navy gets it when they need it, and when they don't need it, they're off. In this case, that's not. So how does the spectrum sharing minimize the interference in the case of these microwave links that are operating 24 hours a day?
Sure. So let's start with sort of the microwave link and then work to the shared access by the Wi-Fi uses. The link locations, the two endpoints of the links are known, the antenna types, the transmit power, heights, other RF parameters, so that we can accurately model not only what that link, sort of how that link performs, but we can model a protection contour around that link based on let's call it an I over N criterion that is necessary to provide protection. So we can model each of these links, and there's actually quite a number. There's well over 100,000 of these operated in the 6 gigahertz band nationwide. We can model every one of them. And with this known protection contour, based on the criteria necessary to provide protection to the microwave link, we can look at Wi-Fi uses and determine whether those standard power Wi-Fi devices will impinge upon that protection contour based on the operating parameters of the Wi-Fi device. So the mechanism is actually very straightforward. Think of it as kind of a query and response. The access point queries the AFC, the cloud-based platform that does the spectrum sharing, over a secure protocol. The AFC then receives information about where the Wi-Fi standard power Wi-Fi device will operate, the particulars around how the Wi-Fi device, its transmit power, and other things, and then it makes a determination, through the propagation simulations of whether it will overlap or interfere or impinge upon the protection contour of nearby links. And if the modeling, which incorporates things like building clutter and other, environmental conditions, if the modeling suggests that there's not an overlap where interference won't occur, then the AFC responds back and says these channels are available. In some cases, there's not a microwave link nearby at all. So the AFC only merely has to check to see whether there's, a link within some proximity that might, be interfered with. But fundamentally, what the AFC responds with is a list of available channels, across the 6 gigahertz band that the Wi-Fi device, the AP, can then select from and, pick and choose which channel it'll operate on. What's great about this is that it also allows for many of the mechanisms that will increase the performance of a Wi-Fi 6 system, like, the more intelligent channel selection algorithms that, are built into the Wi-Fi 6, protocol. So the AFC and Wi-Fi 6 and future Wi-Fi technologies like Wi-Fi 7 and beyond really, are very compatible in terms of how to do sharing with incumbents, as well as maximize the benefit of, new features and functionality, and, in the Wi-Fi, or IEEE 802.11 protocol.
How is this protocol implemented? And now by that I mean, what is it going to be built into the Wi-Fi chipsets? Is it going to be built in on a separate device? Are some devices going to need, I don't know, say an FPGA or an ASIC or something like that? How's that going to be implemented at the device level?
Sure. So one thing, Martin, very important distinction to make here is that the AFC is required only for standard power devices, the higher power category, operating category in the Wi-Fi 6E, or, for Wi-Fi 6E in the 6 gigahertz band. Low power devices, which might include tablets and smartphones acting as a hotspot, for example, do not require that function because they're operating at a power level that the FCC's engineers and industry determined that, through a lot of analysis, that, they believe that that would not create harmful interference to, to the incumbent links. They were more concerned about having some level of software coordination and spectrum management for the high power devices. So this really is more, think enterprise grade Wi-Fi AP that's installed in an arena or a warehouse or covering a university campus. Those devices will support a very simple, lightweight, RESTful JSON protocol. So think of this as a series of HTTPS web calls that the device will go out to the AFC, receive a response, and then check in again once a day to make sure that its frequency assignment is still valid and that the new incumbents haven't come online or something that, would change the operating environment for the device. So very simple sort of, interaction happens over the internet through a secure, for example, TLS-like connection. And this is, a sort of a very simple, software capability that can be built into, the really doesn't need to go down to the silicon level. It could be something part of the software stack that either a module provider or a silicon vendor includes as part of their bundle, or something that the OEM develops themselves as part of their the software that they're putting on top of a maybe a Wi-Fi chip bundle.
I see. So in most cases, these high power devices are going to be fixed locations. So it's
That's right.
mhm.
So think, like I said, those scenarios that I described are probably some of the most, you know, most likely, deployment scenarios: outdoor hotspots, college campus, or campus environments, industrial settings where you need to maybe do indoor and outdoor coverage, or you need to provide coverage to much more expansive areas with one or more Wi-Fi APs.
Can the AFC protocol handle a situation where there's more than one standard power device in a given geographic area? How does that work? And could the protocol break?
Well, I don't think the protocol itself would break. We have, in terms of our implementation of the AFC, which we've actually announced some commercial customers that have committed to use it. One area that we've really focused on is making sure that it can support massive scale, knowing that there will be millions of APs operating at standard power someday, and they'll all need to do check-ins with this database, register and authenticate, and get channel lists and do daily check-ins. So we're anticipating what the scaling requirements will be from the operation of supporting millions of APs through the cloud platform. But I think there was also a part of this question, Martin, is what happens if we find, after this thing gets deployed and there's millions of devices in operation, we're actually causing interference to incumbents? That would be a really unfortunate scenario, and I think one that we've been very careful as an industry to set appropriate protection criteria. But this is the benefit of using a cloud-based technology as the manner to coordinate and share spectrum with incumbents. Through some very simple modifications, we could adjust an I over N criteria, a protection threshold, if we find that whatever is, not we, or say the commission and the industry determines that the current protection threshold is insufficient. Through software, through modifying software, we can completely change the utilization of the band, what and how incumbents are protected. So it's a quite simply a very simple modification to one system, which could completely change the landscape of how the incumbents are protected, and that future-proof capability. And the fact that the system operates closed loop is one of the great benefits that I think we bring. Because if all of this was done on a device level, on an AP level, imagine how difficult it would be to have to go modify firmware or make other adjustments of devices, all these APs that are out in the field, if we find that a change is necessary.
Kurt, can you comment on the status of the commercialization of this spectrum sharing, or on 6E in general? And what do we have? Is everything in place to begin devices coming out on the market, or are there more things that we need? Is there silicon that we need to get there?
So, Martin, all the sort of the key enablers are, very much in place, like silicon, for example. In fact, Wi-Fi 6E low power devices are already in the market. You can buy a 6E router for low power use today, and I think compute devices, tablets, smartphones are now starting to include 6E capability from a client device perspective. In terms of the commercialization path for AFC and standard power devices, a number of OEMs have announced product plans for standard power 6E access points. So that is certainly proceeding. And the activities necessary to bring an AFC to market, to commercialize it, are well underway as well. So this requires a couple things: standards development, as well as a certification program or a test and approval program by the FCC, so that AFCs can be approved and authorized for operation by the FCC we can begin kind of the commercialization efforts. We are, currently in the midst of going through that approval process. We've already begun the first part of that, which is to submit a formal application to the FCC. We're awaiting what they call conditional approval, which is the next step in the process. Then we actually go into the labs and do testing. And as part of that testing, there will also be some field demonstrations that are necessary to sort of show that the technology, is ready for prime time in a real operating environment. And then, following that, the FCC will authorize standard power uses. So very complex, process. There's a lot of details that I sort of glossed over there, but suffice it to say that I think as an industry, we are really on track to, commercialize standard power devices, in the first half of 2023. So, becoming soon.
Kurt Schaubeck, CTO of Federated Wireless, thank you for speaking with us today. For EE World, I'm Martin Rowe. Thank you for watching.